In this video, we're going to look at the derivatives for the exponential functions. Okay, so we're going to start with a specific function. So e to the x turns out to be the best one. So we're going to start with that one. And I'm going to use the limit definition because we don't have a rule that applies when the variable is in the exponent. Okay, so we don't really know what to do here. So we're stuck with our limit definition. So f prime of x would be the limit as h goes to 0, f of x plus h minus f of x all over h. Okay, so for this function, that's the limit as h goes to 0, e to the x plus h minus e to the x all over h. And then using our exponent rules, I know that when I have addition in the exponent, it's like multiplication with the same base. So I could write e to the x plus h as e to the h times e to the x, and that's all over h. Now I see that I can factor out e to the x from the top, so that's e to the h minus 1 left over, all over h. Okay, now e to the x doesn't depend on h, so it acts like a constant, which means that I can move it outside the limit. Okay, so this is actually e to the x times the limit as h goes to 0 of e to the h minus 1 over h. Okay, now notice we still can't evaluate this limit. If I plug in h equals 0, I get 0 over 0. But we can use our old technique of trying different numbers. So let's try and see what this approach is. Okay, so for different h values, okay, I want to see what e to the h minus 1 over h is approaching. So let's start with negative 0.1. Okay, this is kind of close to 0 on the left-hand side. Now I'm not going to show you the work here, but if you plug this in, I think you get 0.9516. Okay, if you do negative 0.01, you get 0.995. Negative 0.001, you end up getting 1 point and a bunch of zeros until you get a number. Actually, no, just that many zeros. Okay, so 4 zeros. And if I get even closer, I get even more zeros. 3, 4, 5, 6. I think there's even more, so I'm going to do dot, dot, dot there. Okay, so it seems like as we get closer and closer to 0, that we are approaching 1. Okay, what about from the other side? Okay, so if I do 0.1, I get 1.0517. If I do 0.01, I get 1.0050. 0.001, I get 1.0001, okay, etc. Again, we can kind of see that it seems like we're approaching 1 this way as well. Okay, so this limit is actually equal to 1, which means that our derivative is just e to the x. So e to the x is its own derivative. So if you want the derivative of e to the x, the derivative is just e to the x. Okay, or another way to write that, d by dx of e to the x, okay, is e to the x. Now, be careful. Maybe I'll do this in a brighter color here. So the derivative of e to the x, it's very tempting, okay, for all the exponential functions, but it's not x times e to the x minus 1. Okay, so the power rule does not apply. Okay, so you cannot use the power rule. You can only use the derivative of e to the x as e to the x. Okay, so the power rule only applies when it's x in the base, okay, and the exponent is a number. So not when the exponent is a variable. So let's do a couple of examples. Okay, so here I have 2 e to the x plus 5 e to the 7. Okay, so using my other rules, the derivative, I can pull out the constants. So this is 2 times the derivative of e to the x plus 5 times the derivative of e to the 7. Okay, now we just saw derivative of e to the x is e to the x. Okay, so that derivative is that. Okay, what's the derivative of e to the 7? Okay, so remember, e is a number, which means that e to the 7 is also a number. Okay, this is a constant, so that means that the derivative is 0. Okay, so this derivative is just 2 e to the x. So don't let anyone trick you. Okay, e to some power, that's just a number. Okay, it doesn't matter that there's an e there, there's no x. Okay, there's no x value. So in the next one, I see that I have two things multiplied together. Okay, so I'm going to let my first function be 3x, and my second function be e to the x. So if I use the product rule, y prime is going to be the derivative of 3 to the x times e to the x plus the derivative of e to the x times 3x, the first function. So the derivative of 3x is just 3, so it's 3 e to the x. The derivative of e to the x is e to the x, so it's times 3x. And in fact, I could simplify this by pulling out a 3 and an e to the x. So it's going to be 3 e to the x times 1 plus x. Okay, so that would be my derivative there. So what about for other choices of a? So something similar happens. Okay, so if this is my derivative of a to the x, we can use our limit definition. So it's going to be a to the x plus h minus a to the x all over h, which is going to be a to the x times a to the h minus a to the x all over h. So I can pull out a to the x and in fact pull it right out of the limit. And I'll be left with a to the h minus 1 over h. Okay, similar to before. Okay, I don't want to go through this again because this actually approaches not a nice number. So it's hard to see what this is going to approach. So you're going to have to believe me for the time being. But this actually approaches ln of a. Okay, now we haven't done the review of the logarithms yet. Okay, but it's log base e of the number a. Okay, it's just a number. Okay, so this is a number. When we get to the chain rule, I'll be able to explain to you why this limit is ln a. But for now, you just have to believe me. So for a function a to the x, the derivative is ln of a times a to the x. Okay, so the derivative of a to the x is ln of a times a to the x, if you want it all in one line. Now, because we haven't done the review, you may not be familiar, but ln of e is 1. Okay, so the e derivative actually follows the same formula, so you could actually replace this a with e everywhere, but ln of e is just 1, so you would still get e to the x. So if you want to just remember one formula, you could use this one. Okay, like I said, once we learn the chain rule, we'll be able to prove this using the chain rule and the derivative of e to the x. So let's just do a couple of examples using this. Okay, so here y prime is going to be, I can pull out the 5, so it's the derivative of 2 to the x plus the derivative of 3 to the 7. Okay, now the derivative of 2 to the x, I just told you, is ln 2 times 2 to the x. And derivative of 3 to the 7, okay, This is 3 times 3 times 3 times 3 times 3. How many do I have? 2, 4, 5. Okay, it's 3 times itself 7 times, okay? I don't know what that number is, but it's a number, okay? A constant. When we want to take the derivative of a constant, the derivative is 0. Okay, so this is just 5 ln 2, 2 to the x. Okay, that would be our derivative here. Okay, what about this one? So f of x is x cubed divided by 3 to the x. So we can use the quotient rule. Okay, so f prime of x is the derivative of x cubed times 3 to the x, minus the derivative of 3 to the x times x cubed, all over 3 to the x squared. Okay, the derivative of x cubed, okay, we know how to do this. This is the power rule. So this is going to be 3x squared times 3 to the x. Now the derivative of 3 to the x is ln 3 times 3 to the x. Okay, and then that's times, x cubed as well. And this is all over, I'm going to leave it as 3 to the x squared, but it's 3 to the 2x if you prefer. Now I want to simplify this. So what do these have in common? Well, I can definitely take out 3 to the x. Actually, I can take out x squared, 3 to the x. Okay, so then I'm left with just a 3 here. The second term, I'm going to have ln 3 times x. And then on the bottom, I have 3 to the x squared. Now I can cancel the 3 to the x with one of the 3 to the x's down here. So this is going to simplify to x squared times 3 minus x ln 3 all over 3 to the x. That's the derivative. So you want to be careful. X cubed and 3 to the x are very different. Okay, so one has the variable in the base and one has the variable in the exponent. Okay, that makes a big difference. You use totally different rules. Okay, so x cubed, you use the power rule. 3 to the x, you have to use the derivative of an exponential function. Okay, so you do want to be very careful when you're computing these derivatives where the variable is. Is it in the base or is it in the exponent?